Hello, everybody. Welcome back. How are we doing today? I hope you're having a great Friday. It feels really good that we made it to the weekend. I finally get to sleep in tomorrow. I'm really excited for that. I hope you guys are as well. Thanks for joining me today. Today is obviously Friday, December the 20th, 2024, and we are 5 days away from Christmas. So, pretty exciting. Um, stuff on that front. I hope your guys' holidays are going well, um, and all that jazz. Let's let the Discord know that we are live here. All right. Let's give it a second to let some folks roll in, and there we go. Hello, Feed. It's so good to hear from you. How you doing today? Well, happy Friday to you. I hope you're well, and thank you for coming back again. It's always so good to hear. Gina, hello. Welcome back. All right. So I thought we would do a quick warm up. Hello, Angela. I appreciate you coming in this evening. Welcome back. Happy Friday to you guys. I thought we would jump right off this evening with a warm up of a practice problem from back in chapter 4, just like we did yesterday, of recursion. So I have this one loaded up. And I will preface that I gave this one a pre-read, and I think that I can actually do this one. I kind of when I chose which one to do, I kind of wrote some stuff down, and I think that we can do this one fairly easily. Angela Michael is The Office. I love The Office. That's so funny you mentioned that. I watched that. I literally just wrapped up watching it over again, and I'll probably start it back soon. It's such I watch it over and over and over again. Yeah, so this problem we're gonna do 1K Flash. Welcome back. How are you guys doing today? I'm so glad you guys joined me on this Friday. Big round of applause to you guys for putting in some time to out of your day today on your Friday to learn some programming alongside me here. And yeah, that's super awesome. Hello, DJ Batman. How are you doing? It's so good to hear from you. I haven't read your name in a little bit. It sounds it's great to hear from you again, and welcome back to the stream. And I hope you're doing great. All right, let's give this one a go. Let's jump into this problem. So I chose this one because A, I think it might be a little bit easy, and B, I think it might be a little bit easy. So let's go ahead. We need a confidence boost when it comes to recursion here. So let's give this one a go. So give a recursive algorithm to compute the product of two positive integers, m and n, only using addition and subtraction. Okay, so when first thinking about this problem, I initially I'm wondering, okay, well, we have two values, and obviously we need to add a value over and over and over again if we're not going to be able to use multiplication, right? We're bound by the use of addition, so we just have to add a variable number of times, a certain number of times, depending on the multiplicative factor of one of these integers. So I think just to keep things consistent with what we've got so far, I'm going to just determine one of these variables as my multiplicative factor and use it as my scale down, right? So if I say def, we will say product, right? And this takes in m and it takes in n, right? These are both integers, and we return a integer, right? Oh, it's just one arrow like that. We return an integer. So I'm going to try to get in the habit of using the type hints. I go in and out. I'm so inconsistent. I use them for like a week and a half, and then I'll stop using them, and I need to pick them back up and use them again. So if I ever If you ever find me, it's annoying that I'm not using them, please let me know and remind me, and I will use them again because they are very helpful. Okay. All right. So, like I said, is I'm going to just assign in my own head here the value of n as our multiplicative factor in this problem, right? With the value that we're going to determine how many times we're going to recurse or how many times we're going to, call product again to create that multiplication effect. So if I just say um, if n is equal to 1, we want to return n, no, we want to return um, m, right? So if n is equal to 1, meaning that we're multiplying these two values together, we just return m, or the value that's being multiplied by 1, because in this case, remember, n is our factor we're multiplying by. Just, we could have chosen m to be that factor and used it vice versa, right? But okay, so then if we say else here, we need to call product of m, and then n will be decremented down by 1, or decreased down by 1 on every call. Um, and so we are then going to add to this the value that was returned. So return m. So this is going to be, we're going to just add m here, right? The current value of m at this recursion to the previous one, right? And so we will return this value. Now, if I'm not crazy, I think that this might be we don't have a condition for 0, right? So if n equals 0, so if n is equal to 0, return 0. Can we say, is this going to be an elif statement, right? Would this be an elif statement? If that elif, it's this, return m, else do this. Okay, if, yeah, probably. I always get confused on whether or not we would have an elif. So, even in all these, in all of these um, months of learning this, this is still like a concept I struggle with, is when to differentiate. So I know that if we call if, each one will be checked no matter what. But in the chain, if one of these is met, it will stop at that point. So that's what the if else chain is, right? It'll go through this chain. If one of these conditions is met, it will stop and do that condition, and it will not follow through anything else. So if we wanted to explicitly do multiple checks, we would have to do if, right? Okay. So I think this is fine. Because if it's 0 right off the bat, then we can return 0. If it's 1, we can return m. Else, we're going to return the value of m that's currently at our current step in recursion, plus that deeper value returned back. So let me quickly pull up the whiteboard. Right. Your analytical thinking / problem solving skills are mad impressive. I'm not gonna lie. Good shiz, bro. Oh wow, that's so nice. Um, that's so nice. Thank you so much. Okay, so let's just first test this out. Print product of um, let's do 2 and 10, right? So this should give us 20. Boom! Let's go. We need an if statement here. So that's all. Yeah, like I said, as I get confused on when the need for the chain, but so if it's zero, we'll return zero. Else if it's one, we'll return m. Else just do this. I would this not? I don't. Can you explain to me why that wouldn't be correct then? Oh, because if it's zero, we don't need to do the other checks because right away we can return zero. If it's one, we don't need to do the other checks. We don't need to do the else because, right, it's this. So, I mean, I could just say if here as well. I mean, I think it'll do the same thing. Elif is also fine in this case. Cool. So then let's put a zero here. Um, so what if we have a zero here, we get obviously zero back. But what if I say zero here and two? What do I get? Zero back. Okay. Okay, because it does this for one recursion down and adds zero and zero basically and gives me zero back. So that does work in this case. So I wouldn't need to say if n equals zero or m equals zero. Okay, cool. So let's make sure this works for bigger numbers. So what about like 100 times 100, right? 10,000. Cool. Wow. Let's go, guys. Yeah, see, I picked this one. Don't get it twisted. I did pick this one on purpose because I was scanning through them. I was like, oh, this one doesn't seem too hard. I kind of jotted some notes down on paper about my thinking, and I was like, okay, let's go. I think this one wouldn't be too bad. So when I was preparing for the stream, so this one was not too bad at all. Um, I would personally do if as a style thing, but the elif is fine. Okay, cool. 1K Flash, I'm glad it's making it easier for you to understand. That's perfect. And thanks so much for joining Snapple as well. I appreciate you coming in and leaving some messages and some energy here in the chat and in the channel. Appreciate you guys. If you guys are enjoying it, feel free to throw it a like, follow along the channel. This is all about just us coming together as peers to learn together in a peer-to-peer setting and really grind through this realistically. Okay, so what about this one? Let's try this guy. Now I'm going to preface, I didn't do any notes on this one. This one's going to be raw. So this one's going to be, this is the first time I've ever read this problem. Now let's try this one. Write a short recursive Python function that takes a character string s and outputs its reverse. For example, the reverse of pots and pans would be snap and stop. Okay. So if we need to, we are going to first define reverse. And it's going to take in some string s. String from stir. It's going to return a stir. Right, perfect. So our base case would be where the length of the string is equal to 1, where we then need, right? So if length, well, first save it as variable, n is equal to the length of the string, right? If n is equal, or is less than or equal to 1, in this case, if n is less than or equal to 1, we want to return the last value in the string, right? So if we return string at index 0, so this will return, in this example, the s back to our previous recursion, where it will be received in our else statement here by some sort of call to reverse for um, we need to slice the string, so it'll be s of 1 forward. So this is going to first take the P in pods, move forward, take the O out of to go from there, then go from the T, then go from the S, then go from the ampersand, then go from the P, then go from the A, and so on and so forth. ASCII, isn't there a quote not empty instead? Not sure. What do you mean by that? I'm not exactly sure. Can you give me a little bit more detail? Thank you so much for your message, though. I appreciate you. Okay, so we're going to return the last value. So in pots and pans, we would return, or the only value in the list. So actually, we don't want to, can't be less than, because the length we don't want to return. So this has to be is equal to 1. We return the 1 value. So this return the s, and then what do we need to do to this value? So the s gets returned, and this function, we're going to, what do we need to do to it at this point? We need to, I think obviously it's going to reverse. We need to put the returned value in front of all the other values. So it becomes, yeah, the return value goes in front of no, because this is what's being returned as s sub 0. Instead of counting the number of characters, if s is not empty, s is not empty. If s is not empty, then we would, well, we just need to capture the length because we need to have a base case that's met, right? We need to know when we've successfully reached all the last character in our string, and then we can, um, and then we need to put it in front of these other characters. So this is iterating down through the string each time until we get one character in the string. So would this just be plus string s here of because in the else statement, if we're taking the p, it would take the p and place it I don't want to do anything with the p. I want to leave it. Hmm. So return s, right? Like Theed says, if we can just return s in the first if statement, we'll return that value of literally s here. Okay, so don't get confused. We're returning the string s, which happens to have this last value of s here, which is what it will be. So in pots and pans, we return the s here. What would be a, so then we need to take, hey Roshan Brooks, I appreciate you coming in. Yeah, this was a PDF I found online. I also provide it in the. It's either you can look it up online for yourself, or I also provide it in a Discord linked below, where I just provide all of my study resources that I'm using live on stream. So I'm trying to think what we're gonna do here. So let's think, for example, the P is gonna. It's not gonna meet this, so it's gonna get entered into this. We're gonna add the strings 1 through 0 to S. The reverse of, okay, so we're gonna add the slicing. So in the first recursion, we're gonna take the P. No, we're not gonna take the P. Why are we taking the P? No, we're just gonna go down further until we get to the S. The S gets returned here as this value. What if I say S dot append here? So that will append this value to this gets returned here. No, because the S append will add it to the end of the previous recursion list, which would be ends, and then it'll become at the end. And they'll add that at the end. Take the last character S at index -1 and concatenate it with the reverse function. So if we take the index of S at -1, the last item in our sequence at this point, and concatenate it with the return, no, we need to do it on the opposite side. Like so. So if I call print reverse on quote pots and pans, what do I get? S. Oh gosh. Okay, so now what if I put it on the other side? What if I return this? I still get S. So we're successfully capturing the S. And then, but in each time we're taking S and adding it to S. So no, we want to take S of the one index, right? Of, so we need to place the P yes. Yeah, exactly. Not what we were looking for. So we were just adding, right? We were just adding the last one. So in each recursion, right, we're getting pots and pans. So the S was still the last one. Then it's aughts and pans. The S was still the last one. So we needed to add. We needed to append. So S gets returned, and then out of aughts and pans, we need to take the n, we need to... Bradley Bell, I'm not sure what that syntax means. Could you explain that one? So this returns the S. We're concatenating it with... What do we need to concatenate it with? We need to concatenate the S with the N to get snap. Then we need to concatenate it with the A. Dang it. So we're taking the S and we need to add to it -1 minus N. So in this case, N would be 1, so we take the last one. Oh, shoot. Type error, bad operand type for urinary. Urinary plus stir. Okay. Oh, whoops, I have a plus out front, that's why. So what about this? String index out of range. Returns the whole list. Last -1 is the step, so you should return the list in reverse. Are you supposed to manipulate the string? I'm not sure. This is all the only prompt we were given here, Leon. I appreciate your question, though. Yeah, Bradley, that's what I was about to say. We are using recursion explicitly here with this example, so we'd have to call the return value, right? Or call the function again. But no, I appreciate your help so much. Thank you. You're helping me think this through. So right now, if we add the negative first, let's think about this. Okay, we're breaking pots and pans down to, let me get my whiteboard out. My white boy out. Whiteboard. Okay, so we're breaking pots and pans, right? So we're first gonna take this, we're gonna look at this value, we're gonna call the function, and we're gonna take the last value S and add it to the last one that's returned. So we're breaking this down all the way at the end of our recursion. We're taking S at reverse of 1, we're returning S, right? The string, quote S. That's all that's left. We need to, if we add to that value, like I'm doing here, the -1, we're just going to add S over and over and over again. That's why we're getting the snake, right? Because we're just, in each recursion, whether we take out the P, take out the O, take out the T, take out the S, we still have the S here at the end, which is the -1. That's what's happening here. So we need to add the -1 minus N. So at this point, it's minus... So N would be 1. What about this? Ooh! Woo! That's what I'm talking about. Woo! I knew it. I knew we had to use N. Oh my gosh, let's go. That was so cool. I just, oh, I got the, I guess got the, a premonition. I'm so sorry if I blew your guys' ear out there. Solved that one. Woo! Let's go. That was so good. right? Because we need to take negative n here, right? Because we need to, if n at this point is 1, n at this point is 2, 3, 4, we want to take the negative n, the negative n, the negative n each time. Let's go! We're getting better at this! Oh, I'm screaming in the apartment right now. The walls are shaking. Oh, that was cool. That was cool. That was a channel moment right there. I might need to make my first little my YouTube short and make that a short. That was so cool. Oh, awesome. Right. We don't want to take the negative 1 every single time. We want to take the negative n because we'll take the previous one, the previous one, the previous one each time. Oh, that was so cool. Oh, I'm on like cloud nine right now. I feel really happy and proud. That was so cool. You guys, that's what she said. Oh, you guys helped me solve this one for sure. Give yourselves a round of applause right there with me on this one. Awesome. Okay, cool. Let's dive into the rest of chapter 5 here. Would you be able to explain how you did this? Yeah, no problem. Let's go through it. No worries at all. Let's go through this one. Okay, so we're solving this problem here. Let me make my screen bigger, and then let's also. Is there a way to zoom without? My chat GPT hotkey isn't working. Chat jipped. Now it works. There we go. Can you wait? How to zoom in VS Code, not make font bigger. Control plus plus key. Okay. No. Command plus. Okay, here we go. Okay, so our goal with this function was, our problem was to write a short recursive Python function that takes a character string s and outputs its reverse, right? For example, the reverse of what happened here? The reverse of pots and pans would be snap stop, right? Okay. So we need to do a recursion function, we have to take in some input, and we have to break that input down into a base case, right? We have to reduce that input down to one single condition, whatever that may be, tailored to the certain problem. So that's where we do have to be a little bit creative, is we need to come up with these base cases. That's what I think makes these hard, is that you A, have to understand what's being returned when the function is called, and B, you have to understand if you have the right base case. So with a string, for the instance of pots and pans, right? That's the string we're using in this example. To break a string down each time, rather than calling the string in the reverse function, we are going to call it, right, the string, but we're going to call it one character forward than the first character each time. Remember, because strings are zero index. They start from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8 for their iteration values, right? Or index values. So in this case, every time we call this reverse function, we're going to be calling it from the next character over. So in the first call, we're going to call it for the total string. So all of pots and pans. And the next call, we're calling it for 1 through, which is that we're taking a slice from index 1 on, which would be from the 0, or the O, aughts and pans, right? And then we're taking tts and pans, and then we're taking sp and pans, and then we're taking and pans, and then we're taking pans, and then we're taking ands, and then we're taking n's, and then we're taking s, right? So each time we're lessening the string by one value until we reach a base case where the string has a length of 1, right? So we take the string, we determine its length at each iteration through the function, we check if that string is 1. If it is, we have reached our base case, and we just return that value, right? And think about this. If the string that was provided was only just one value, let's say of s, well, you can't reverse a string of one value, so you would just return the string, right? You just return, and the s, which the string of quote s in reverse is just s. There is no reverse of a single character, so that makes sense for our base case, right? That's just a double check. So we return s in this case. So let's just take this for example. So we have our string in the first iteration. We have pots and pans. Okay, we move to the next one. Aughts and, right? T all the way through, S all the way through, ands all the way through, pans all the way through, ands all the way through, ends all the way through, and then finally the S. Okay, we met our base case, and so don't get this confused just because this is an S right here and this says an S. These are two different things. We're returning the string S that has a length of 1. By convenience and by coincidence, the string, the last character in it happens to be S. So just keep that in mind. That's not what we're returning here in this statement. We're returning the string, which has one character in it, which happens to be, at this example, S. So the S gets returned, right? And so with recursion, when the return value, how I think of it is it just gets replaced for this function. That's all that's being done, because when you unfold the recursion, this return value gets replaced as this for each previous level or outside recursion step or higher level recursion step. So the S, or just the string, or in this case quote S, is returned as this entire statement reverse through the length of 1, right? Because we iterated down, we called this function, we came back through, we determined that it was 1, and we returned S back to this function, right? It was called within the initial call. At this point, we add it to our string index of -n. Now this might seem confusing, but what we're doing is I tried to write it out on my whiteboard here. Oh. Right, I tried to write it out on my whiteboard here, where we have pots and pans, right? We are first gonna we're gonna slice until we reach our base case of S. We return that value of S, right? And then we add to it at that instance, at that recursion level, whatever it is at that step, the current string that we're working on, right? Plus, or not, no, sorry, the current string that we're working on, the index of -n. So this might be confusing if you're really, really new. I'm going to try my best to explain it. Again, I'm not a teacher. I'm a learner. I'm a peer. So I'm just trying to explain this how I understand it here. If any of you else have other opinions or clarifying statements, feel free to provide. So the last character is returned in our base case. We add to that the string character at -n. So we need to then, I'm going to quickly just Control Z to get rid of all of those cancels, right? We returned the S, right? And then we back to the previous statement. And if you remember, the previous statement had cancels for all of these other ones except for the N. It was just the N and the S were the ones remaining with a length of 2. So we had to call this function again. So that's what it was returned to from the base case. The base case was returned to that previous, recursion step, which was N and S. And we append to it the S at -n. And if you think about this, whiteboard, in this case, right, at this recursion step, our N, or our length of this string, is equal to 2. So in the previous example, we were just adding -1. So at every time we were just adding s over and over and over again because s always remained our -1 index or the last value in our string, for every recursion step. But we needed to add the the um, the -n index value as the string shrunk down and down and down. So now for the -2, we return the n. So the n then gets placed here, right? Snap. Then in the previous recursion step, we have n equals 3 at this a, right? A, n, and s is n equals 3, right? So, and then we take the -n, which is -3, 1, 2, 3. We take the a and put it here. Snap all the way through until we take the ampersand, then we take the s, then we take the t, then the o, and the p, and we get snap stop. So that was my best to try to draw it out. It's a lot of things going on at once with these recursion traces, but hopefully that helped. That was my thinking through it. What do you guys think? Yeah? Good? Hopefully we're all good. All right. Okay, let's go ahead and back this up. There we go. It's a little bit small. Let's go like that. There we go. Okay, nice. Great explanation. Oh, great, awesome. I tried my best. I know I am not the most technical. Again, like I say, guys, I'm learning this live with you. So take what I say with a grain of salt. Do your own independent research and things like that. But yeah, that Python's right. Yeah, thanks so much, boy. We just solved this one. It was really fun. I appreciate you for stopping in and leaving a message. Or as a voyo. Yeah, no. Thanks so much. Okay, let's jump down into chapter 5 here. So if you guys remember, in chapter 5, we left off on 5.4. We just finished 5.4. I think we were moving on to 5.5, if I wasn't mistaken. Pattern matching. Here we go, yeah. Using array-based sequences. Hey, Theed, how's it going? What's up? Try SABC. Okay, let's try it. CBA. We got it. Our function's good. Learning Python right with you. Awesome. Thank you for going live. No, of course. This is exactly what this is for us to be hanging out together, learning this, grinding this out with, a companion alongside you. It's much easier to do with someone else, I think, than on alone. Yeah, so we get to do it together. Yeah, we got this one right. Awesome. I'm so happy for that. Cool. Let's get into 5.4. I made a mistake here. No worries. Let's pull up. I'll just pull up my answer real quick for you here. So this was, if you need to take a picture or a screenshot or something, this is the answer that we got here. So I'll just leave this up for about 5 more seconds. Let you take a screenshot or something if you wanted it. Again, guys, just also actually really quick, I'll just I'll push this to GitHub. Yeah. I'll just push it. So if you guys want these notes, just go down in the link below in my GitHub and grab them. Also, if you want the PDF for the book I'm reading on the right side and all the other books and resources I'm doing on stream, you can join the Discord, which is completely free, no cover charge, no nothing, completely free. Just a community, another place for us to talk offline and network and stuff. So it's great. Let's say. Completed more chapter 4 practice. Continued on to chapter 5. All right, here we go. Okay, 5-5. Using array-based sequences. Storing high scores for a game. Okay, cool. We're going to get started with an example here. The first application we study is storing a sequence of high score entries for a video game. This is representative of many applications in which a sequence of objects must be stored. We could just as easily have chosen to store records for patients in a hospital or names of players on a football team. Nevertheless, let us focus on storing high score entries, which is a simple application that is already rich enough to present some important data structure concepts. To begin, we consider what information to include in an object representing a high score entry. Obviously, one component to include is an integer representing the score itself. We identify a dunderscore method, get dunderscore, or a self dunderscore rather, pardon me. We identify a score as dunderscore, right? Not underscore score. Another useful thing to include is the name of the person earning the score. We identify this as underscore name. So these are just two attributes assigned to our class of name and score, where the game entry that says the person's name and the score. Just like if you run an arcade game and you see the credits roll by and then it shows all the top scores. This is where we're getting that example from, like on an old arcade. We could go on from here, adding fields representing the date the score was earned or the game statistics that led to the score, etc., etc. However, we omit such details to keep our example simple. Perfect. In a Python class, game entry representing a game entry is given in code fragment 5.7, right? So we call class game entry. So we're creating a class called game entry, which will initiate objects for game entries. In this class, when we initialize, we provide a name for the whoever ran this had this high score, and then we also have the score saved. We have a function where we just return the person's name. We have a function where we just return the score, and then we have a dunderString method, which is the dunderStir method is when called, and you can actually print the function. This will just display this object in a string form. Normally, from my understanding, is that when you call objects that don't have a dunderStir or a dunderRepr method, repr as in like represent, or I'm not sure exactly, but the repr method is usually used to, like, you can just copy and create new objects, so it's just like a literal copy of the code to create the object again. But that's from what I kind of understand. But the stir would just be, if you call a function without the dunderstir, it gives you like a memory location, or what would it be called? It's a memory address, right? It's memory address within your system. So we have to give it a string so that the Python knows that this memory address is associated with this string, just to represent it, right? Think of like a baby that hasn't been named yet. It first pops out of the womb, and then it has to be assigned a name, or it's just called baby, right? Okay. Sorry for that example. That was the first thing that came to my mind. Can you try another example like A, B, C, D? Yeah, of course. D, C, B, A. So do you guys want me to try to like go over? It seems like there's a little bit of confusion, and I want us to be all on the same page here. Okay, so let's just take the string example, quote A, B, C, and D, right? A, B, C, and D. So we're calling, I'll just use R as my function, right? We're calling reverse on, quote, A, B, C, and D, okay? Within this function, you can see with just a general, a general thing of recursion functions is you have to reduce the input somehow. So I've learned that with strings, you can reduce the input by slicing from the index 1 on, leaving off the first value every single time. So that will continually shorten the string by one integer. Or sorry, not one integer, but one integer in length, we'll say, or one character. So now we call the recursion for the slice. I'll do a 0 right here. 1, 2, 3, right? For a total length of 4, right? Cool. We call recursion again for 1 over. So quote B, C, D, close quote. Boom. With index value now 0, 1, 2, which equals to a length of 3, right? We call recursion again. Boom. Of quote C, D, right? With an index values of 0 and 1 for a total length of 2, right? 2 values in our string, length of 2. Okay, we come down again. Our base case is not met. We have a length, not a length of 1, we have a length of 2, right? R of quote D from 1 over, right? 1 over, 1 over, right? Of just D now, okay? Our base case is met, and our value, quote D, is returned to this previous function, okay? Is returned as this previous function, right? The D, quote D is being returned as this entire function. So I'll do that again. Quote D is being returned as this entire function. Okay. Within the body of this function, we take what is returned, right? And we add to it s at index of negative n. Okay. So back over on our whiteboard, we're adding to D, right? D is what it represents, this entire thing, and this entire thing on our left side is being added to s at index negative n, or string index negative n. Well, our n value is equal to 2. Remember, this is 2 values in our string here. It's equal to 2. Right? So we would go, this is negative 1, this is negative 2. We would take the C and we would add it to D. Okay? This entire tuple or whatever, new list, right, string, is returned as the entire value of this previous recursion step. So this is quote D and C. Okay? And we're adding to it a string of negative n. 3 is our n, negative 1, negative 2, negative 3. B is our negative 3. That gets added right here for quote D, C, plus quote B. This entire thing is returned back to the first iteration, where then A is added onto it for a negative 4 length. Boom. Right? Hopefully that helped. I got really jumbled really fast, but I went slow and tried to really talk slow through it and make things clear. Let me know if that helped you out, Faris, or anybody else. Let me know. Just for a shorter example of ABCD. Awesome. Great. I'm so glad that helped. Yeah, General Talks, we hit 500 subs. Yeah, it's so crazy. So I thank you guys so much if you're subscribed and following. You know, we have a lot of people that consistently come into the stream day after day. I stream trying to every day. I'm really taking this seriously. So if this is something that you're interested in and want to join along and are passionate about as well as I am, then follow along and let's do this together. That's the whole point of this. I appreciate you guys being here. Consider liking the stream so we can get some other people to maybe find it, and get a bigger community of everybody in here. It'd be so cool to have a big community of just programmers all working together, right? The more ideas, the merrier. Okay, let's jump back into chapter 5. Awesome. I'm so glad that helped you get it. Thank you so much for being here and for asking that. That was great. I'm sure that helped other people to get that breakdown. Cool. Pardon me. Let's shake up the lava lamp here. Let's get this lava in. Lava in. Lava in. It needs to get a little bit warmer. Got to get that to melt. I want to get like a big lava lamp for the stream that we can have in the background, like a big like rocket ship one. I think that'd be cool. I don't know. Okay. A class for high scores. To maintain a sequence of high scores, we develop a class named scoreboard. A scoreboard is a limit to a certain number of high scores that can be saved. Once that score limit is reached, a new score only qualifies for the scoreboard if it has strictly a higher than the lowest high score on the board. Okay, so we're just making a scoreboard, exactly. The length of the desired scoreboard may depend on the game. Perhaps we have 10 slots or 50 slots or 500 slots. Since that may vary depending on the game, we allow it to be specified as a parameter to our scoreboard constructor. Internally, we will use a Python list named underscore board in our order to manage the game entry instance that is being represented that represents the high scores. Since we expect the scoreboard to eventually reach full capacity, we initialize the list to be large enough to hold the maximum number of scores, but we initially set all entries to none. By allocating the list with a maximum capacity initially, it never needs to be resized, right? So this was like what we talked about before for having a tuple. Now this we can't have a tuple though because the advantage of having tuples in lists was tuples have a predetermined size that is never changed. They're immutable, meaning they can't be changed, right? So, but if we pre-assign a list to have a predetermined length and that doesn't change, then we can also have that same effect in memory, essentially. So, let's keep going here. By allocating the list with a maximum capacity initially, it never has to be resized or dynamically have another dynamic list created. As entries are added, we will maintain them from highest to lowest score starting at index 0 of the list. We illustrate a typical state of the data structure in figure 5.18. So an illustration of an ordered list of length 10, storing references to 6 game entry objects in the cells from index 0 to 5, with the rest being none. So think of this as like an old arcade game where where after you get done completing the level, it displays all the high scores to you, right? Now, each game entry is just a person and their score. So as you can see, these are the scores, and they're in ascending order would be ascending or descending, decreasing order from 0 to 9, index 0 to 9, right? So the highest score would be 0, the lowest score would be towards the end of the list. Got you. A complete Python implementation of the scoreboard class is given here by the command given in code fragment 5.18. The constructor is rather simple. The command self underscore board, right? So we just take we create a list with a default with a single value of none and multiply this by capacity, which this is a Python shorthand trick of saying we just want to create none times the capacity. So create this none object 8 times. So we'll have 8 nuns in the list that we can then fill with high scores. So creates a list with the desired length, yet all entries are equal to none, right? Because we then can override them with the high scores, like with a list. If we did this with a tuple, we could not edit those high scores, and then this would not work. So that's why we need to use a list here. We maintain an additional instance variable underscore n that represents the number of actual entries currently in our table. For convenience, our class supports the getItem method to retrieve any entry at given index of syntax board at index I, or none if no such entry exists. We support a simple stir method that represents a string representing the entire scoreboard with one entry per line. Okay, so this is our scoreboard class. When we initialize, we assign a capacity. So we have this has 10 spots that it can have as high scores. So we got a question here. Mina Habib says, in your reverse example, why didn't you use s index 0? Wouldn't that be equivalent to s in minus n every time? So let's think about that. Let's pull up our whiteboard. And feel free to ask questions and question what I'm doing. If I'm getting things wrong or if I'm wrong, I would love to figure that out and go through this. Don't shy away to asking stuff. This is a peer-to-peer discussion, you and me. This is not some sort of not any pressure or any. Take all that away. This is friend to friend, peer to peer, learner to learner. We're on the same level here. Okay, so if we had a quote ABC and we call this down to quote BC, and then we call this down to quote C. If we added to it and we returned C for all of this, I mean, yeah, I guess you could, right? What about for a longer example? So if you just do 0 here, you get the same thing, right? Snap stop, yeah. It's same thing. So I bet you this is probably the easier way of thinking about it, right? You could just take the first value every time. Exactly. Which happens to also equal the negative n in that case. I just did things harder for myself, I guess. Cool. Awesome. That's good to know. I'll say like this. Or you can also plus also plus s0. Instead, in place. There we go. Cool. All right, let's continue on here. Hey, Vanch, thanks so much for coming in. Good to hear from you. Awesome that you're back again. Thank you. Welcome back. Okay, so when we set this board up, we create a board with a capacity of none. Board just represents a list, the list, right? And we have a n value, which just houses the actual number of high scores that aren't none in this list. And currently, we have a list of all none values, so no high scores. We have a getItem, which just returns the index value. Okay. We have a stir, which just gives a physical representation, like a string value of what this is. So we create a new line and we join that every new line we join to it the string board at index j plus range for j and range of the value of scores that are in there. So this will just print at every new line the name of the high score. So board or all of the high scores, I guess. We add a score. To just add a score, you just do entry get score. Where's the get score method? It's applied to this. Joseph asks, are you building a game? No, not right now. This is just an example given in the data structures and algorithms book that we're reading live here on stream. This is just an example going over, arrays and things like that. Okay, adding an entry. The most interesting method of the scoreboard is the add, which is the responsible for considering the addition of a new entry to the scoreboard. Keep in mind that every entry will not necessarily qualify as a high score. If the board is not yet full, any new entry will be retained. Once the board is full, a new entry is only retained if it is strictly better than one of the other scores. Exactly. In particular, the last entry of the scoreboard, which is the lowest of the high scores. When a new score is considered, we begin by determining whether it qualifies as a high score. So if we increase the count of active scores, or the underscore n method, right? So if we originally had 5 high scores, and now someone else played the game, and now we have 6 high scores, and because we can fit 10s, we have 4 more spots that by default that can be filled just with any score. Unless the board is already at full capacity. In that case, adding a new high score causes some other entry to be dropped from the scoreboard, so the overall number of entries remains the same. To correctly place the new entry within the list, the final task is to shift any inferior scores one spot lower, with the least score being dropped entirely when the scoreboard is full. This process is quite similar to the implementation of the insert method of the list class, as described in pages 204 and 205. In the context of our scoreboard, there is no need to shift any none references that remain near the end of the array, so the process can proceed as diagrammed in figure 5.19. So, where we have these original scores of Mike, Rob, Paul, Anna, Rose, and Jack, Jill comes along and plays the game and scores a 740. So she gets placed at this index 2. Paul, Anna, Rose, and Jack all get shifted down to index 3, 4, 5, and 6 finally gets filled because now because we had 4 empty blanks, and now because Jill played, we have 3 empty blanks. Perfect. To implement the final stage, we begin by considering index j is equal to self of n, so the amount of scores minus 1, which is the index at which the last game entry instance will reside. After completing the operation, either j is the correct index for the newest entry, or one or more immediately before will have a lesser score. The while loop at line 34, so we have a while loop at line 34 here, so we shifts the scores rightward to make room for the new entry. Okay, while j is greater than 0, and self.board index j minus 1 gets score and less than score. Okay, so then you take that index j and you set it equal to what it would be at the same index but 1 less. Okay, and then minus j each time. Interesting. While the while loop at line 34 checks the compound condition, shifting references rightward and decrementing j as long as there is another entry at index j minus 1 with a score less than the new score. Sorting a sequence. In the previous subsection, we considered an application for which we add an object to a sequence at a given position, while shifting other elements so as to keep the previous order intact. In this section, we use a similar technique to the sorting problem, that is, starting with an unordered sequence of elements and rearranging them into non-decreasing order. The insert sort algorithm. Okay, here we go. Okay, we're learning an algorithm here, guys. Wake up. Here we go. The insertion dash sort algorithm. We study several sorting algorithms in this book, most of which are described in chapter 12. As a warm-up, in this section, We study several sorting algorithms in this book, most of which are described in Chapter 12. As a warm-up in this section, we describe a nice, simple sorting algorithm known as insertion-sort. The algorithm proceeds as follows for an array-based sequence. We start with the first element in the array. One element by itself is already sorted. Then we consider the next element in the array. If it is smaller than the first, we swap them. Next, we consider the third in the array. We swap it leftward until it is in the proper order with the first two elements. We then consider the fourth element and swap it leftward until it is in the proper order with the first three. We continue in this manner with the fifth element, the sixth, and so on until the whole array is sorted. We can express the insertion sort algorithm in pseudocode as shown in code fragment 5.9. So we take in some array A and we call the insertion sort algorithm on it. Input, right, array A of n comparable elements, and then output the array A in rearrange in non-decreasing order. So for index k from 1 to n minus 1, do the following. Insert A at index k at its proper location within all the bounds all the way up through k. Go. Hey Lambda, how you doing? Appreciate you coming in. This is a simple high-level description of insert sort if we look back at the code fragment 5.8 of section 5.5.1. We see that the task of inserting a new entry into the list of high scores is almost identical to the task of inserting a newly considered element in insertion sort, except the game scores were ordered from high to low. We provide a Python implementation of insert sort in code fragment 5.10, using an outer loop to consider each element in turn and an inner loop that moves a newly considered element to its proper location relative to the sorted subarray of elements that are to its left. We illustrate an example run on the insertion sort algorithm in figure 5.2. The nested loops of insertion sort lead to an O of n squared running time in the worst case. The most work is done if the array is initially in reverse order. On the other hand, if the initial array is nearly sorted or perfectly sorted, the insertion sort runs in O of n time because there are few or no iterations of the inner loop. Okay, so you could have like an amortized O of n time if you don't have to do too many operations of sorting. Okay, so this is what's going on. Cool. So this is the Python code for the insert sort algorithm. Let's go here. Let's do like this. Go Python, and then go down. I think that's how you copy code, right? Or do code. And we'll say def insertion underscore sort for an algorithm A, right? We're going to say for k in the range of 1 to the length of the array. So if the length of the array is 5, we're going to index from 1 to the length of the array. So we're not going to examine the first value, right? Because the current value, if k is only, the length is only 1, then k0 would already be in sorted order. Okay, so we save a current value is equal to a at some index value k provided. And we say j is equal to k here. While j is greater than 0 and a of j minus 1 is greater than the current value. So while j is greater than 0, meaning that we have values to actually iterate over, and a at index j minus 1, so the previous value is greater than the current value, we set the array at index j equal to array at index j minus 1. We decrement j by 1. Then outside the while loop, we set the array of j to equal the current value. And this is where the code will end. Right? There's a lot going on here. So we're looping over all of the values for k. At this point, we set j equal to k and keep track of j is going to reference the previous value. Okay. And it continually, so it sets j to equal the previous value, and then it loops j all the way down to all the previous values and does those swaps. Okay. So this is what's going on. So B, C, A, B, no move. A gets swapped all the way to the front. Yep, E gets swapped, no move. H, no move. G has to get swapped. And then the F will have to get swapped as well. Okay. Simple cryptography. I'm sure we'll get some practice with this one soon enough. So if that was, this one's, I'm kind of understanding what's going on here, but we definitely need some practice, and we'll get some soon enough, hopefully. Simple cryptography. An interesting application of strings and lists is cryptography, the science of secret messages and their applications. This field studies ways of performing encryption, which takes a message called the plain text and converts it into a scrambled message called the ciphertext. Likewise, cryptography also studies corresponding ways of performing decryption, which takes a ciphertext and turns it back into the original plain text. Arguably, the easiest encryption scheme is the Caesar cipher, which is named after Julius Caesar, who used this scheme to protect important military messages. All of Caesar's messages were written in Latin, of course, which already makes them unreadable for most of us. The Caesar cipher is a simple way to obscure a message written in a language that forms words from an alphabet. The Caesar cipher involves replacing each letter in a message with a letter that is a certain numbers of letters after it in the alphabet. So, in an English message, we replace A with D and B with E and C with F, and so on by shifting by 3 characters. We continue this approach all the way to W, which is replaced with Z, and then let the substitution pattern wrap around, so that we replace X with A, Y with B, and Z with C, converting between strings and character list. Given that strings are immutable, we cannot directly edit an instance to encrypt it. Instead, our goal is to generate a new string. A convenient technique for performing string transformations is to create an equivalent list of characters, edit the list, and then assemble a new string based on the list. The first step can be performed by sending the string as a parameter to the constructor of the list class. By the example of list quote bird produces the result quote b comma quote I comma quote r comma quote b or d in a list. Conversely, we can use a list of characters to build a string by invoking the join method on an empty string with the list of characters as the parameter. For example, we can call the empty string.join with bird to returns the string quote bird. Okay, the join method joins all of the values in the array as a string. Okay. Oh, as you can do as a string. Okay. Using characters as array indices. If we were to number our letters like array indices so that A is 0, B is 1, C is 2, and so on, we can write the Caesar cipher with a rotation of R as a simple formula. Replace each letter I with the letter I plus R. Mod 26, where mod is modulo operator, which returns the remainder after performing an integer division. This operator is denoted with the percent sign in Python, and exactly the operator we need to easily perform the wraparound at the end of the alphabet. For 26, modulo 26 is 0. 27 modulo 26 is 1, and 28 modulo 26 is 2. The encryption algorithm for Caesar's cipher is just the opposite, so we replace each letter with the one R replaces before it with wraparound. That is, the letter I is replaced by letter I minus R, mod 26. We can represent a replacement rule using another string to describe the translation. As a concrete example, suppose we are using a Caesar cipher with a 3-character rotation. We can compute a string that represents the replacements that should be used by each character from A to Z. For example, A should be replaced by D, B by E, and so on. The 26 replacement characters in order are D, E, F, G, I, all the way through A, B, C. Okay. We can subsequently use the translation as a guide to in the encryption message. The main challenge is how to quickly locate the replacement for each character of the original message. Fortunately, we can rely on the fact that characters are represented in Unicode by integer. Fortunately, we can rely on the fact that characters are represented in Unicode by integer code points. The code point for the uppercase letters of the Latin alphabet are consecutive. For simplicity, we restrict our encryption to uppercase letters by integer code points, and the code points for uppercase letters of the Latin alphabet are consecutive. For simplicity, we restrict our... Okay. Python supports functions that convert between integer code points and one-character strings. Integer code points, one character. Specifically, the function ordc takes a character string as a parameter and returns the integer code point for that character. Conversely, the function chrj takes an integer and returns its associated one-character string. In order to find a replacement for a character of our Caesar cipher, we need to map the characters quote A to quote Z to respective numbers 0 to 25. The formula for doing the conversion is J is equal to ordc minus ord quote A. So ord takes a one-character string as a parameter and returns the integer code point for that character. So ord t would be 84. Why would t be 84? Ord A is going to be 65. Which is 19. What? A sanity check if character C is quote A, we have the J is equal to 0, where C is quote B. We will find that its ordinal value is precisely one more than for A, so the difference is 1. In general, the integer J that results from such a calculation can be used as an index to our pre-computed translation string. I'm going to be honest, this does not make a lot of sense to me. In code fragment 5.11, we develop a Python class for performing a Caesar cipher with an arbitrary rotational shift and demonstrate its use. When we run this program, we perform a simple test and we get the following output. Secret message is this, and its message is the eagle is in play, meet at Joe's. So Caesar cipher, when we initialize, we give a shift. We create an encoder, which is 26 characters long, and we create a decoder, which is 26 characters long. for the index value in the range of 26, we set encoder at that index equal to, yeah, this is really, I'm not really sure what's going on here, you guys. This one's a little bit funky. Got really jargony really fast here. Let's just keep going though. This doesn't really seem too important, like, for our purposes here. Oh, we were on 5.5 already? Oh, this was 5.5. I should say using array-based sequences. We went over this Caesar's cipher here, and it just got really jargony here. So we can represent a replacement rule. Let's go back up. So I get you need to calculate the modulo to do the wraparound. But ORD takes a one character string and as a parameter returns the integer code for that one pointer. The ORD function in Python takes a single Unicode character as an input and returns the corresponding integer ASCII Unicode code point. A single character string of length 1, integer representing the Unicode. Okay, so it's just a specific code associated with them. And so they use all capitals because they all correspond, they're all consecutive. Okay, so they use this to just determine the order here. So A minus T be W. Here's the replacement for T. Okay. Let's keep going here. Oh, whoops. This is... Wait, what the heck just happened? Okay. Let's go copy this guy. If you guys are enjoying and following along, please, if you guys wouldn't mind, maybe throwing the stream a thumbs up or following along to the channel. We've been growing, and I really appreciate you guys joining and being here and helping me out learning these things. It's really awesome that you guys are here with me doing this too. Okay. Multi-dimensional data sets. .6. Multi-dimensional data sets. Okay. All right, lists, tuples, and strings in Python are one-dimensional. We use a single index to access each element of the sequence. Many computer applications involve multi-dimensional datasets. For example, computer graphics are often modeled in either 2 or 3 dimensions. Geographic information may be naturally represented in 2 dimensions. Medical imagery may be provided in 3-dimensional scans of patients and company valuations. And a company's valuation is often based upon a high number of independent financial measures that can be modeled as a multidimensional data. A 2-dimensional array is sometimes called a matrix. Okay, a matrix. A 2-dimensional array. We may use 2 indices, say I and J, to refer to cells in the matrix. The first index usually refers to a row number and the second to a column number, and these are traditionally zero indexed in computer science. Figure 5.22 illustrates a two-dimensional data set with integer values. This data set, for example, represents the number of stores in various regions of Manhattan. Okay, so an illustration of a two-dimensional data set, of a two-dimensional integer data set which has 8 rows and 10 columns. The rows and columns um, are zero index if the data set were named stores. The value of stores 3, index 3 and 5 is value 10. So 3 and 5 is 100. Okay, so 3 is the column, no, is the row, and 5 is the column. Okay, row, column, row, column, row, column. Okay, and the value of row 6, column 2 would be 632. Got you. A common representation for a multi-dimensional array set in Python is a list of lists. In particular, um, we can represent a two-dimensional array as a list of rows, with each row itself being a list of values. For example, the two-dimensional data set 2, 18, 7, 5, 23, this row, this one might be stored in Python as follows. 22, okay, so you do a list, so each row, got you. Row your boat. Okay, so it'd be like, um, a list of lists represented in Python as a list of lists, where each list is a row, is a new row in the matrix. So we'll do example, and we'll say, we'll copy this, so 22, 18, 709, 5, 33, 45. We'll have to make this go down. 45, 32, 830, 120, 750. So we'll need to space these out a little bit. So, and then we'll do 4, 880, 45, 66, 61. Like that. Oop. Cool. Would be written as follows. Data is equal to a list of lists. We'd have 22, 18, 709, 5, 33. The next list you'd have 45, 32, 830, 120, and 750. And then in the next list, you would have 4, 880, 45, 66, and 61. Like that. Data at index value, let's say, what, 1, 0 would equal, so row 1, 0, 1, and then index 0 would be 45. So we say like data with a row, column, like that, right? Data index for row, we'll do row 2. Lists are 0 index, so the first row and quote column in the matrix are accessible, are in the matrix are index 0. Okay, so column 2 or row 2, let's say 0, 1, 2, 2, 2 would give us a value equal to 830, right? Like that. Cool. Awesome. An advantage of this representation is that we can naturally use a syntax of data 1, 3 to represent the value that has row index 1 and column index 3 as, so that would be row 1, column index 3, 0, 1, 2, 3 of 120. As data 1, the second entry is in the outer list, it itself has a list and thus indexable. To quickly initialize a one-dimensional list, we generally rely on syntax such as data 0 times n to create a list of n zeros. On page 189, we emphasize that from a technical perspective, this takes a list of length n with all entries referencing the same integer instance, but that there was no meaningful consequence of such aliasing because of the immutability of the int class in Python. We have to be considerably more careful when creating a list of lists. If our goal were to create the equivalent of a two-dimensional list of integers with R rows and C columns, and to initialize all the values to 0, a flawed approach might be to try the command we create 0 times columns times R. Warning, this is a mistake. While the list of 0 times column indeed creates a list of C zeros, multiplying that list by R unfortunately recreates a single list with a length R times C, just as 2 times 4 creates 2 of those. Okay, got you. It just extends them by doubles it. Okay, a better yet still flawed attempt to make a list that contains the list of C zeros as its only element and then to multiply it by R. That is, we could try the command data equals some list with a list inside times Z times R. This is much closer, as we actually do have a structure that is formally a list of lists, but the problem is that all R entries of the list known as data are referenced to the same instance of a list of C zeros. Figure 5.23 provides such a portrayal of aliasing. So if we initially create a list, so a flawed representation of a 3x6 data set with a list of lists created with the command 06 times 3. So we create a list of 6 zeros, and then we have 3 separate lists that reference all of those objects. Okay, this is truly a problem. Setting an entry such as data 20 equal 100 would change the first entry of the second list to reference a new value 100. Yet the cell of the second list would also represent the value data 00 because row data 00 and row data 2 refer to the same secondary list. Yeah. Okay. A valid of a 3.x6 data set of list, for simplicity, we overlook the fact that the values in the secondary list are referential. To properly initialize a two-dimensional list,
we must ensure that each cell of the primary list refers to an independent instance of a secondary list. This can be done by this can be accomplished through the use of Python's list comprehension syntax. For list 0 times c for count. So we do make a list of zeros, make a list of 0 and multiply by the c count. So we'll have 6 zeros or 5 zeros in the list. For j in range of r. This command produces a valid configuration similar to the one shown in figure 5.24. By using a list comprehension, the expression list 0 times c is reevaluated for each pass of the embedded for loop. Okay. Therefore, we get our distinct secondary list as desired. We note that the variable j in the command is irrelevant. We simply need a for loop that iterates r times. Interesting. Okay, so this is how you'd create this two-dimensional list from scratch. So we'll come over here, come into here, go like this, and make a to initialize a two-dimensional list would be data is equal to times c for j in range of r. So c would be the amount of columns and r would be the amount of rows. Okay. Yeah, zeros across the top and then r's for the amount of lists for the rows. Got you. Okay. Two-dimensional arrays and positional games. Many computer games, be they strategy games, simulation games, or first-person conflict games, involve objects that reside in a two-dimensional space. Software for such positional games need a way of representing such a two-dimensional board in Python. The list of lists is a natural choice. Tic-tac-toe. As most school children know, tic-tac-toe is a game based on a 3x3 board. Two players, X and O, alternate by placing respective marks on the cells of this board, starting with a player X. 4 days until Christmas. Oh, awesome. Yeah, it's crazy. It's coming up really, really fast. Anybody have any cool Christmas plans or vacations coming up that they're excited for? Hello, Angela Lopez. Thanks for coming in today. How are you doing? All right. Um, If either player succeeds in getting 3 of his or her mark in a row, column, or diagonal, that player wins. This is admittedly not a sophisticated positional game, and it's not even that much fun to play since a good player O can always force a tie. Tic-tac-toe saving grace is that it's a nice simple example of showing how a two-dimensional array can be used for positional games. Software for more sophisticated positional games such as checkers, chess, or popular simulation games are all based on the same approach we illustrate here for using a two-dimensional array for tic-tac-toe. Interesting, okay. Our representation of a 3x3 board will be a list of characters with X's or O's designating a player's move or an empty string space designating an empty space. For example, the board configuration 0xO would probably list 0xO, blank string X blank string, and blank string 0x. We develop a complete Python class for maintaining a tic-tac-toe board for 2 players. That class will keep track of the player's moves and report a winner, but it does not perform any strategy or allow someone. We develop a complete Python class for maintaining a tic-tac-toe board for 2 players. That class will keep track of the moves and report a winner, but does not perform any strategy or allow someone to play tic-tac-toe against the computer. The details of such a program are beyond the scope of this chapter, but it might nonetheless make a good course project. Before um, presenting the implementation of the class, we demonstrate its public interface with a simple test in Code Fragment 5.12. So we have a game, which is some class called tic-tac-toe. We have these marks, and then we print winner. Winner equals game.winner. If winner equals none, print tie, else print winner wins, right? So these are the marks that they're made, okay? This is just a test of this tic-tac-toe class being run. The basic operations that are a new game instance represents on an empty board that the mark I and J represent, it adds a mark at the given positions for the current player, with the software managing the alternating of turns, and the game board can be represented with the winner determined. The complete source code for the tic-tac-toe class is given in Code Fragment 5.13. Our mark method performed our mark method dot mark okay our mark method performs error checking to make sure that the valid indices are sent and the position is not already occupied, and that no further moves are made after someone wins the game. So we have a class tic-tac-toe. When we initialize, we create a board with empty string spaces with three columns for J and 3 range 3 for 3 rows. We have a function called mark, which just marks the position on the board at index I and J, or column and row, or row column, I'm sorry. It puts an X or an O at the position IJ for the next player's turn. If not between these values, meaning we print back value here, that means it's not a valid position on the board. If self._board is index J does not equal a blank spot, we raise a value error saying it's occupied. Right? If the winner is not none, we raise a value error saying the game is complete. Okay. We self.board at index I is equal to self._player. If player is equal to quote X, if player is equal to quote X, self.player equals quote O, else okay, so is win are all these different conditions. It checks these are just the winning conditions that are checked, right, for diagonal, column 1, 2, 3, reverse, diagonal. Winner returns the mark that won, and then the string represents the board. Okay. Oh wow, and that's the end of the chapter. Oh, crazy. Wow, awesome, guys. Cool. So that is the end of the arrays chapter. Now, I will be going back through in some extra time I have in, these next few days, just here and there, and just polishing up my notes and adding in some additional things. I didn't do the greatest job of taking notes this chapter, just because it was a lot more conceptual things like, definitions and understanding, what's going on in the memory and stuff. So I will go back through and take some more notes just to polish things up, but that is the end of chapter 5. Wow, moving through things pretty quickly here. Going to be going through on to 6 sooner than later. Spending New Year's home this year alone. That can't be all that bad. I mean, let's you can grind some Python. I'll be doing some streams over the break, that's for sure, so we can at least learn some Python. So this one has 12 reinforcement problems to do. Awesome. So we'll do like maybe 6 tomorrow and 6 on Sunday, and then be done with these, and continue on with the chapter 6, stacks, Qs, and DQs. Interesting. Wow, awesome. Okay, you guys. Let's go ahead and shift focus to the small business manager for a little bit. And yeah. Let me go ahead and save this up. Okay, so we have a program that does what it's supposed to do basically. It takes in items and we can find and edit each one of those items and do various things to them. The next goal in our project here would be to, if we go to the add item menu, that just makes this. Um, so we need to be able to exit out of this menu at any time if like we want to go back. So let's go to the add item menu, run add item. So we're going to run set name. Hmm. So what value can they add? That's the thing that's kind of tricky is once they're in this menu, they have to add an item. Hmm. Hmm. Because it's doing all of these calls here. Oh, okay. I'll have to think about how I want to go about this one. Because we can't just say, like, oh, if they press Q, because all of these are different functions, right? Hmm. Okay, well then, if we can't do that right now, then what can we do? Let's see here. If we run, enter in, and go inventory. So obviously we need a view. So let's go ahead and set up a view, I guess. Okay. Um, do we want? I kind of want to skip past the view because I kind of want to set up a time to look into like pandas and import pandas into our project and display things, in grid format and stuff like that using pandas. Um, so that's why I'm kind of delaying doing the visual right now. Hmm. So we could do the transactions menu. Sorry, I'm yawning. It's been a long week, you guys. I've been tired. Doing a lot of late night streams and getting up early for work and stuff. It's just it's been a little tough. So I might call things here around 9 o'clock today, and then maybe get into some other possible uh, like tomorrow we'll really take some time to polish up this project when I'm got some more sleep and energy here. Okay. So we need the transactions menu ran. So transactions like sales and transactions. So I'm trying to think is should we what do you guys think? Should we put the transitioning of items from one um, you know instance, for lack of a better word, to another within the inventory menu, or should we put it within like a transactions menu? I'm just I just don't want the user to also think the transactions menu is for like expenses, like transactions that are made for expenses. So we can make like a sales menu or like a so inventory. I don't know. Maybe we should keep it in the inventory. So if we have inventory here, um, this just has the find, edit, view. So we have the find and edit. Do we want to make like a find and transact menu? So if we make this, instead of find slash edit, we make this find ampersand edit. We make a quote find ampersand transact menu, right? So if we enter into this, so that'll create, so if we enter, we'll say elif
So we'll say
match user input, and we'll say case is one, quote one. We run this function, right? Case quote two, we're going to run this function. Case quote three, we're going to run this. We're going to run the find the run case. We're going to run find edit transact item. Sorry, I'm yawning so much, you guys. And then case quote four, we'll run the view inventory method. And then if case case quote five, we're going to run system again. Hey Angela, thanks so much we got two Angelas here. This project is the Small Business Manager. So for those that are new or may not know, after I do live learning through various means of data structures and algorithms, or all the other books I'm reading, or maybe some videos or something, I will then transition into the back half of my streams, or especially on weekends when I have a lot more time. Like I do say, I'm a chemist in my job. I have a 9 to 5, and so I do this after my 9 to 5. I study and learn, but on the weekends I have a lot more time, and so we really get to actually work on these projects. So I try my best to actually have projects lined up that correspond with the learning that we're doing, so we can actually implement them into some real world applications. So this project is a small business manager where a business manager with little experience in managing inventory items, transactions, expenses, things along those lines can download this Python file, load in their items into via these item object classes. Those items are saved into as these items in these files. When they run the program, those files are read and loaded into the system, and then they can make edits on the items. They can edit the names and the parameters that they assign when they created the instances. They can transact these items into for sale. They can list them for sale, and then they can transact the for sale items into sold items. So you can so, and then based on that information, that gives you a lot of data of the life cycle of the item within the business, from in inventory to being for sale with having a date listed and a for sale price, to being sold to having a sold price, so you can calculate like a discount provided or anything like that. um, Now we will say we probably need to think about those discounts and stuff that might need to be saved. So we probably have to edit our class to add in some more attributes and necessary information needing to be saved by the user, discounts and things along those lines. But yeah, and eventually, hopefully, we can get to actually provide the user with, income statements for various filtered out months or years or quarters or whatever. We can provide them expense reports. We can provide them, all sorts of various tax information associated with their business or their performance. And so it might seem fairly simple, or maybe no one will use it in the future, but I think this will also provide a way, as me not having with it, not me being someone not with a computer science degree, but with a physical science degree in human biology and chemistry. I have to be able to provide, projects and real world application to showcase my skills rather than having a degree or certificate. If I were to ever try to transition into this field, or, showcase my skills to an employer that might be in, both the physical and, computational science fields and computer science. So I want to have these projects at A, to, reinforce my learning and continue, B, to practice, and three, to have, physical assets that I can bring to the table for maybe future employers, or just any sort of general case of where I might need to show my skills and what I can do and provide. And if I can say I, wrote and designed an entire software system from scratch that, manages business inventory, expenses, transact business, you know, sales transactions, and then provides detailed accounting reports in the form of these documents, and saves rights. It would be pretty impressive, I think, in my opinion, if I was able to create the system. So, little by little, day by day after the streams, we're really building on top of one another to create this project and insert my learning. It's really starting to get dense now. We're kind of past the point where we're really taking on like not a lot of new and maybe quote unquote easier topics. And so everything that we learn now is maybe taking us a little bit longer than before, because we're starting to take that step into that intermediate to maybe more looking at some more advanced topics, rather than just going over, for loops again, or variables, or basic functions and stuff like that. We're kind of moving past those basics, and really kind of polishing and refining our skills now on a more Pythonic and a deeper level. So I'm going to go ahead and call it for tonight here, you guys. It is Friday. Gonna just hang out and enjoy my evening, but I will be back on a stream tomorrow. I might do either like a double feature, maybe an early morning and a later night one, or maybe just one long one in the afternoon, depending on how I'm feeling. But we will do a lot of work on the project this weekend. So please follow along to the channel and subscribe. We've been growing like crazy, and it's so awesome seeing the channel growing and seeing all you guys participating and wanting to be involved and showing a lot of positive feedback. Join the Discord link below, where I have all my study resources, and we can communicate offline and network, and showcase our projects. And then I'll be here tomorrow. And I also announce my streams, like what I'm going on in the Discord and stuff. So thank you guys so much for joining this evening. I'll see you tomorrow. Today we finished chapter 5 in data structures and algorithms, and then did a couple of recursion practice problems from back in chapter 4. Feeling a lot better on recursion. We were able to solve 2 of them on our own pretty quickly, so that felt really good. And yeah, so things are moving along nicely, and little by little, we're building that foundation we need to learn. So thanks so much for joining me. Um, interact with me in the Discord.